Welcome to another podcast. In this episode, we're going to be taking a look at a second problem involving series solutions. Once again, we're expanding around ordinary points. And the equation that I have in mind is a fairly famous equation. If you look at a lot of differential equations textbooks, you're likely to see this equation talked about. I won't give the name of it yet. I'll tell you its name toward the end of the video. But the first thing we notice is that we have a non-constant coefficient. So the coefficient x in front of the y term here, this is non-constant. It's the first time we've worked a problem with that. And because of that, we can't use the characteristic equation here. This is why we're studying the things we are in this unit. We'd still like to know what are the solutions of this differential equation. And in order to do that, I'm going to guess that the solution is a power series, and I'm going to center it at the point 0, simply because if you look at the equation, there is nothing wrong with x equal to 0 as an expansion point, since it is an ordinary point. Once again, we write down the values of y prime, even though we don't have to plug it in, just so we can correctly give y double prime before we make our substitution. So this is kind of always the first step. Go ahead and write out the variable in terms of y. If we plug it in, so we'll start here with, we're looking at the sum, let's see here, n goes, and I'll go ahead and shift the indices here all at once. I want to shift this to be n equal to 0, so we've got the sum n equals 0 to infinity of, this becomes n plus 2, n plus 1, a n plus 2, xn minus x times y. Y is the sum, n goes from 0 to infinity. It's just the basic power series here. So all I've done is substitute in for y double prime minus x times y equal 0. That's what I've substituted in for the original equation. My next step here, I'm just going to rewrite what I have. And I'm going to pull the x inside the equation here. So remember, because x right here does not involve n is the indice, I can move it in and out of the sum formula if I'd like to. It's essentially distributing the x to this infinite polynomial. So now we have the sum, n goes from 0 to infinity of an x to the, this now becomes n plus 1. So here's where things get a little bit trickier. I would like to have the indices match as well as the powers for x match. And notice that as of right now, even though I have the indices matching, the powers of x do not match. So the only way that I can really address this is if I pull out a term that's a part of this polynomial. And the best way to do that is by shifting this indice to begin at 1. So adding 1 to the indice is going to subtract 1 from everything, including getting the power down to xn. And then I want this power to come up to n equal to 1, but notice if I shift the indice up, that's going to shift the power down to n minus 1, and then I have the same problem all over again. So what are you going to do? Well, the easiest thing to do is pull out, specifically pull out the n equal to 0 term. So if I plug in n equal to 0, I have 2 times 1 times a2. 2 times 1 times a2, and this would then be x to the 0, which is 1. So this represents what you get when n is 0 from the sum. And then I start the sum at 1. And so what you notice is I've got my powers are the same. So now the powers are the same, and the indices are the same. When that occurs, I can then group everything the way I want to. So we've got the constant term. Sorry, I'm writing kind of small here. There's going to be a lot of work on this problem. And because the indices are the same and the powers are the same, I can group this sum. And I have n plus 2, n plus 1, a n plus 2, minus a n minus 1. All of that times xn equals 0. So this is going to imply two things. The first thing it's going to imply is I need 2 times a2 to be 0, or I need a2 to be 0. Or the second thing that it implies is I need my recurrence relation, n plus 2, n plus 1, a n plus 2 minus a n minus 1. I need this piece to be equal to 0. Solving for the highest power is going to, or the highest coefficient order, n plus 2 in this case. This is my recurrence relation. And the first thing you notice is there's no negative over here, so we're not going to have the pesky switching of the positive and negative like we did on the previous example. And one thing I want you to understand here is that this is valid starting at n equal to 1, 2, 3, and so on, because that's where my sum begins. So I had two equations come out of this. I have a2 equal to 0, and I also have the recurrence relation. Now, if you look at this recurrence relation, it relates a n minus 1 with a n plus 2, making this a 3-step recurrence. Because it's a 3-step recurrence, I have to be careful. I need a 0. I need to know what a0 is. I need to know what a1 is. I also need to know what a2 is. It turns out a2 is 0, which is going to imply that a5, a8, a11, all of these are going to be equal to 0. So understand that what we're basically doing is, if it's a 3-step recurrence, we're breaking the numbers from 0 to infinity up into terms that are divisible by 3 with certain remainders. So we would call this doing this operation modulo 3. If you look at a0, a0 is going to be the generator for the sequence a0, a3, a6, a9, a12. a1 is the generator for the series a1, a4, a7, a10. And a2 is the generator for the series a5, a8, a11. Because the generator a2 is 0, all the rest of the terms in the sequence that it generates are also 0, which is to be expected here. This is a second-order differential equation, so really I should only have 2 free variables, which suggests that these are the only 2 things I need to describe the solution. Now I'm going to look for the values of the a0 sequence and the a1 sequence, just like I did on the previous problem. So I'll show you, for example, if I do a3. So a3, according to this, is a0 over 3 times 2. That would mean that a6 is also a0, but it's over 6 times 5 times 3 times 2. Notice we skipped the 4 there. Then that would lead us to a9 being a0 over 9 times 8, 6 times 5, 3 times 2, and we skipped over the 7. All of this is leading us to a description of a3n. These are terms that are divisible by 3. Those terms are a0 over 2 times 3, 5 times 6, all the way up. And you see that the 2 largest values here, 9 and 8, are 3n minus 1 times 3n. So this is a description of the numbers that are on the bottom. They're grouped 3n minus 1 and 3n for whatever the subscript value is. Now, here's the problem. I don't recognize this pattern. It's not one of the power series functions that we're used to working with. Let's see if doing a3n plus 1 can help. So if I start with a1, the next term I would get is a4. So a4 is a1 over 4 times 3. a7 is a1 over 7 times 6 times 4 times 3. Notice we skipped over a 5 there. And that leads a10 to being a1 over 10 times 9 times 7 times 6 times 4 times 3. Once again, I don't recognize this, and in fact, If I was to find a 3n plus 1, these are all terms that are divisible by 3 with remainder 1, then you would have a 1 over basically the same thing. We would start with 3 and 4, so you'd have 3 times 4, and in general the pattern is 3n and 3n plus 1. I know that's hard to see, but it's 3n plus 1 there, because those are the last two. 10 times
it doesn't do me a lot of good here to
plus
write
1
these
times
terms
1
down
less
like
than
I'm
that,
going to
which would
show
be
you here.
We'll have
So
y
I
of
don't
x is equal to
recognize
if I look at the a zeros,
this pattern
it's
either.
the sum n goes
This
from
one's
1
sort of
to
a new one
infinity
for us.
of this piece here. So we've got an x to the 3n over 2 times 3, 5 times 6, all the way up to 3n minus 1 3n, plus the a1 term. Goes from 1 to infinity. We've got x to the 3n plus 1 over this stuff. Those are the only terms that survive. And as I was saying before, it doesn't do me a lot of good to write that down, even though that technically is the answer, because I don't recognize what these are. On the previous video, we knew that one of them was the power series expansion for cosine. We knew the other one was the power series expansion for sine. I don't recognize these functions. Just because we don't recognize them doesn't mean they don't have names. They do. This first one is called the Airy function. So this is the Airy AI function. So Airy AI of x is the power series expansion for this. And the power series expansion for this is typically called Airy BI of x. And if you've ever solved a differential equation in Maple on some of these Maple labs we've done, the idea is that these are written in terms of an integral, but these often pop up in Maple. So these are functions that you might see in Maple, which is just a fancy way of saying that they aren't functions that have a nice closed form expression. In fact, both of these are written in terms of integrals, and they're very complicated looking functions, but they're also incredibly important for various physical phenomenon. And so you've got the Airy function, Airy AI of x, and Airy BI of x is what these actually are. A better way to write the final answer here, though, is just write out the first couple of terms of each expansion. So I'll do that now. If I look at the power series expansion here for the Airy AI function, the first couple of terms are 1 plus x cubed over 6 plus x to the 6th over 180 plus, and it keeps going. And to get these values, notice all I'm doing is coming back up here where I calculated A3. A3 was A0, and then it was 1 over 6. And then here I've got 1 over 180 and so on, plus A1. A1 is x for the first term, x to the 4th over 12, and then x to the 7th over 504. And that keeps going. And the one last comment I want to make is notice that the final answer here is of the form A0 times a y1 plus A1 times a y2. And there's a theorem called the ordinary point theorem that says if you're solving an ordinary point equation, all of them wind up being this exact same form. You have the value A0, which remember is y at 0. So remember from here, y at 0 is A0. And then you have y prime at 0 is A1. Those end up being the two constants that are in the problem. And if those constants are known, if those values are known, then we can solve the IVP in this case using the fundamental set y1 and y2. Now I have not proved to you that these form a fundamental set of solutions. We could do that using the Wronskian and looking at the determinant of these two, but they do indeed form a fundamental set of solutions. So area AI and area BI are the fundamental set of solutions using the series solutions method for this differential equation y double prime minus xy equal to 0. So that inclusion of x made a big difference here. And this is a 3-step recursion. It's got a little bit of everything in it. So this is a good example for you to look at as you're starting to work through some of the problems in this chapter. All right, thank you for watching.